In this example, we have a 1.6 meter long cantilever supports a concentrated load of P equals 18 kilonewton. So the beam is made of rectangular timber having a width of 120 and a depth of 280. Calculate the maximum bending stress due to the applied load at a section located at 0.5 meter on right of restraint A. Okay, so we have this cantilever beam as shown here. So we're calculating the maximum bending stress due to the applied load at a section located 0.5 meter here. Okay, it is 0.5 meter. We're calculating the maximum stress on this section. Okay, of course, the equation will just be maximum bending stress or normal stress because of bending equals bending moment times C over I. Right? This is a cross section. It's easy to find out the centroid. Right? So the C to the top and C top and C bottom will be the same, right? Because this is a symmetric cross section, right? And the I is just I equals just what B h cube over 12. Here in this case, the B is 120. H is 280 cube over 12. Okay, so this is so we can calculate this number very easily. Right, so I start from here. We just need to find the M, right? So we can calculate I very easily. We can determine C very easily. So we just need to find out M. What is the M at this cross section? Okay, how to find the M value? So we have to draw the moment diagram. Right? So for drawing the moment diagram, we need to determine the restraint forces, etc. Right? So we have those steps: free body diagram, equilibrium equations, etc., to find out the maximum bending moment and the moment diagram through this cantilever. Okay, so let's start from the free body diagram. Okay, here, cut it here, make it free. So we have AX, we have AY, have M at here. Right, then obviously AX equals 0, right? So AY, how about AY? So AX equals 0 and AY equals P, right? Since you have only one concentrated load, that is 18 kilonewton. Then M, that we need to do a sum MA equals 0. So based on this, we have M plus P times L equals 0. So M equals negative P times L, 18 times 1.6, that is negative 28.8 kilonewton meter. Okay. Is the bending moment negative or positive? I look at the shape, right? After this loading, it will cry, right? This is negative, right? A crying thing will be negative, right? Negative bending moment. Then, so based on this, we can draw the diagram, right? The diagram. So, okay, from this original loaded cantilever, let's draw the V diagram first and then M diagram, right? Okay, what is the V at point A, you have AY, right? AY upward, so that is a positive value. That is 18. So between A and B, you have nothing. So we just keep a constant. To point B, then you will encounter a downward P that is 18, right? So it will be reduced down to 0. Okay, this is the V diagram. Okay, the constant value 18 through the whole cantilever. Okay, so what is the area? The area will be just 18 times 1.6, that is 28.8, right? Then we can draw the M diagram. Air diagram, the M diagram, so on point A, the value M is what? Negative 28.8. Right? Negative 28.8. And from A to B, we will add this area, 28.8. So it will be just a straight line connecting A and B. Okay, so this is our M diagram. So we're determining what? We're determining the M values at a location 0.5 meter from point A. Okay, we're calculating the M value here. Okay, how to determine this? You can calculate the area here, right? So just use negative 28.8 plus this sub area, right? So M at 0.5 equals negative 28.8 plus 18 times 0.5. Right, so this will be negative 19.8 kilonewton meter. Okay, so you have another choice. That is to calculate this value from similar triangles. Okay, you can try to do this by yourself, but I'm sure you will get the same results. Right? Otherwise, I made a mistake, or you will make a mistake. Okay, this is similar triangles. Try to solve it and get the same result. That is negative 19.8. Okay, then according to our algorithm, in the second step, we also need to determine the y bar and I, right? But y bar is easy to find since it's just in the center, right? So C top and C bottom will be the same. That will be just a half of the height, 140 millimeter. And the I will be just 120 times 280 cube over 12. That is 219.5 million millimeter to the fourth. So after that, we can just calculate the last step. We can calculate the maximum stress. Your request is to calculate maximum bending stress due to the applied load at this section. Right, so this will be just the M 0.5 times C over I, and this will be 19.8, right? The 19.8 we just determined. Million, okay, times 140 over 219.5 million. Okay, so why we need this million here? Okay, be clear that we're using this million to convert kilonewton meter to Newton millimeter. Right? From kilonewton meter to Newton millimeter. Okay, then here will be millimeter, and here will be millimeter to the fourth. Okay, so here the result will be 12.63 is directly megapascal. Okay, because of the symmetry, this is the symmetric cross section. So on the top, it will be in tension or compression. Okay, this is negative bending moment, right? Negative bending moment, it will be deformed in such a way so that on top it will be in tension, right? The top fiber will be stretched, and in the bottom it will be in compression. It will be in compression. The fiber will be shortened, right? So on top it will be tension. So positive 12.63 MPa, and on the bottom it will be in compression. So negative 12.63 MPa.